The character appearing in this work is fictional. Any resemblance to real persons, such as the President of USA, is purely coincidental.
This is Barack. He started programming and he likes computing big datasets. He has a problem. He is using serial programming, and this is way too slow for Barack. This makes Barack angry. But you see, Barack did some research and found out about parallel programming. The main idea behind how parallel programming works is based on the fact that a number of threads or processes execute multiple tasks simultaneously. In other words, the computation is concurrent, whereas in the case of sequential programming, the execution of tasks is done step by step until the end of the program is reached. Back in the late 1950s, the interest for parallel computing started to grow, leading to the implementation of supercomputers from the 60s and 70s. These machines primarily used shared memory multiprocessors, meaning that a number of processors were executing together on shared data. This means that they were allowing communications between programs that are accessing them. Moreover, in the mid-80s, there was a new kind of parallel computing machine developed, leading to the observation that extreme performance can only be obtained using massive processors. As a consequence, the MPPs, also known as massively parallel processors, were developed and have continuously grown in size and power, giving rise to today's multi-core processors. Although parallel computing will increase performance, having programs computed in parallel doesn't necessarily mean that the runtime will be proportionally lower to the number of processors. For instance, if executing a code on one processor takes 20 seconds, running it on two processors will not yield 10 seconds. Respectively, if you run the code with four processors, it will not yield 5 seconds. For this matter, Amdahl's law steps in, dividing the structure of a program into two sections: the serialized code and the sections of code that can be parallelized. As seen in this equation, the speedup depends on the proportion of code that cannot be parallelized, the variable s, the percentage of the code that is computed in parallel, the variable p, and the number of processors, the variable n. In the case of a serial implementation, the problem is divided between a discrete series of instructions or tasks. Furthermore, these instructions are executed one after the other in a sequential manner and on a single processor. This means that only one instruction can be executed at the same time. On the other hand, parallel computing is done on multiple devices or processors in order to solve a problem. Generally, parallel computing is based around the idea that the problem is divided into smaller parts that can be computed at the same time. Furthermore, if each of these parts is separated into a series of instructions that are executed simultaneously on different processors. As a consequence, a control mechanism is required. However, not all code sections can be parallelized, and also the parallelization does not provide a significant improvement in performance. This aspect will be presented in greater detail in the following sections when certain implementations will be explained. Now let's go back to Barack and see what parallelizing software does he want to try out. The first one is OpenMp technology, which relies on the forked join execution model. Basically, a software program that is implemented using OpenMp starts out with a single process, also known as the initial thread or the master thread. This thread executes the code in a sequential manner until the first parallel section is encountered. Afterwards, the master thread creates a number of threads. All the threads execute the tasks that make up the parallel section in a concurrent manner. The tasks executed by each thread are defined by the specific code found in the parallel construction. After the end of the construction is reached, the master thread will terminate the other processes and is the only one that resumes the execution of the remaining program. The second method is known as MPI, which stands for Message Passing Interface. It represents a technology that depends on a portable message passing mechanism. A number of methods are usually used when executing an implementation based on MPI. To begin with, after importing the corresponding library, the MPI init method constructs the global and internal variables. Furthermore, a communication context is constructed for all the processes, and also the unique ranks are assigned to each process. The MPI comSize method is used in order to determine the number of processes in a context, whereas the MPI comRank method returns the ID of the current process. Based on these methods and the message passing mechanism, parallel computing is achieved. Usually, the execution of the program ends with MPI finalize that has the role of cleaning up the MPI environment. The last method is the pthreads implementation, which yields the best results in terms of parallel computing performance in comparison with the other two methods. Pthreads does not require any intermediate memory copy or message passing because the threads share the same address space within a single process. It's as simple as passing a pointer. The basic methods used by pthreads are pthread create for thread creation, pthread exit for thread termination, and pthread join in order to check the termination of a thread. Other methods which are generally used are represented by pthread attribute destroy in order to destroy the characteristic of a thread, pthread attribute init to assign certain attributes to a thread. Parallel computing has many applications and is used especially when dealing with very large datasets. Two parallelized applications were selected in order to display the characteristics of parallel computing in comparison to their serial implementations. Moreover, these applications will also display the differences between the three technologies previously presented. This image conversion relies on the idea that the three initial color channels of a pixel, red, green, and blue, are converted into other three complementary channels. Y stands for luminosity, whereas U and V are chromatic components. Moreover, each pixel is computed independently, meaning that parallel computing can easily be applied in this case. The equations display the manner in which RGB pixels are converted to YUV pixels and vice versa. Each channel has a separate equation with its own coefficients, and all the results obtained are unsigned bytes, with values ranging from 0 to 255, where each value is a codification for a specific color. Similar to RGB YUV conversion, the RGB YIQ transformation relies on the same idea, only that the complementary channels are Y stands for luminosity, and I and Q are the chrominance information. For this case, a similar process is applied, each pixel being transformed by applying the equations for each of the three channels. OpenMP implementation is similar to the serial one. The directive pragma OMP4 is applied on the for section in order to create the threads that are going to execute the loop clause. A schedule may be applied in order to tell the threads how they should handle the for loop. For example, a schedule of static 50 means that each thread takes a maximum of 50 iterations at each point, executes them, and if any iterations are left, they try to take again another sequence of 50 consecutive iterations. To compile the program, you only need to add the fopenmp flag in the terminal. Next, we are going to talk about the MPI implementation. The first thing that has to be done is to import the MPI library. The entire code is executed by all the processes. To mark a specific area for a specific process, the rank of the respective process has to be called in an if clause. The entire technology is based on messages. It utilizes MPI send and MPI receive to transmit the data. These functions block the process until they are resolved. A more elegant solution is to use the special functions MPI scatter and MPI gather that have to be visible for all the processes. MPI scatter splits the dataset equally, and MPI gather collects all the data. The idea of this implementation is to have a central process that reads the file that has to be processed, determines the number of pixels, and the method to split the image. This central process is responsive for scattering each dataset, collecting the processed data, and finally, writing the output into a file. The last method presented is the pthreads method. It is based on the same principle of splitting the image in equal areas. Again, the first thing that has to be done is to import the pthread library. A structure is created that contains all the information for each thread, like number of pixels, the pixel vector, and the result vector. All the processing is done by using a function. The initial thread sets the necessary information for each thread and then creates the threads. This is done by using pthread_create. Then the initial thread waits for each thread to finish the processing of the data through pthread_join. At the end, it collects all the results and writes the output into a file. As discussed earlier, there are some programs that cannot be easily parallelized. One example is the Gaussian blur filter. As seen in this image, the pixel transformation depends on the pixels around it. This is why this filter is different from the other ones, in which every pixel transformation has been done without dependencies. For this filter, the only viable method is the OpenMp one, because it does not transmit datasets from a central process to the other. Now we are going to compare the times for all the methods. As displayed in this table, the fastest method is the pthreads, which has separate memory areas. The second method is the OpenMP, which uses shared memory. And the slowest parallelizing technology is the MPI. This is mainly due to the fact that it spends too much time on sending and receiving messages. And don't forget that if Barak learned parallel programming, so can you.